Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be talking to you about the common source N-channel MOSFET with source degeneration, where this configuration allows us to be one step closer to building an ideal current source. And today we're going to be looking at the solutions for the input resistance Rn, the output resistance Rout, and the AV gain of this NMOS transistor. In order to do that, we need to consider the small signal of the transistor and what it looks like, and do the small signal analysis. And what it looks like is something like this, where we have Vn and there's VGS here, and there's an RS connected to ground, and we multiply the transconductance by the voltage VGS, and that's in parallel with RO. That goes to RD, and we also have a voltage Vout here, where we can consider that we have a current that flows in here, I in, and a current that flows here as well, IO. And let's consider this current here, IO1. And let's put some inputs, some pluses and minuses. So plus minus the VS here, and this is a plus minus here, VO. And for RO, we have a plus minus here. And now let's consider that Rn, we know Rn is equals to Vn over In. So what is In? So we know that there's a open here, right here. So there's zero current that flows. So In is equals to 0, and we can consider this 1. So as you can see, you can already see that Rn is going to be infinity because In is equals to 0. But let's go ahead and write a KVL, right? Solve for voltages in this loop right here. Okay. And if we do that, we can see that we have another equation, negative Vn plus VGS plus RSIO is equals to 0. And again, that IO is coming back from here. This is IO. So as a result, this is IO. And we then see that Vn is equals to VGS plus RSIO. And this is the second equation. And Rn, let me use blue. Rn is equals to Vn over In, which is equals to VGS plus RSIO over 0 again, which is basically infinity. So that's our Rn for this configuration, this common source NMOS with source degeneration. But then now let's figure out Ro, the output resistance. So in order to figure out Ro, or Rout, we consider that this is equals to Vout over Iout when Vin is equals to 0. So what is IO? IO, we could say IO is equals to IO1 plus GMVGS. And this is using KCL. This is solving for currents. Next, we can solve for IO1. IO1 is just basically equals to IO minus GM VGS. What I did was I moved this to this side. And let's consider this our first equation. All right, so I hope that makes sense. Again, if it doesn't, this is IO coming here. So that IO must equal to this IO1 plus GM VGS. Let me back it up to get rid of that. Now we can consider the next situation, which is going to be KVL at this loop. Let me go ahead and do green. Again, consider KVL at this loop, where again Vn is equals to 0. So again, we get 0. So this is our next. So this is KVL. We get 0 plus VGS because we're going into the positive terminal of VGS plus RSIO is equals to 0. So we can solve for VGS as it being equals to negative RSIO. So this is our second equation. And then now let's do a third equation, which is going to be this loop right here. Let me just go ahead. Maybe I use a different color. I'll go ahead and use blue. So imagine this loop here going to ground. So we get minus VO, and again, this is a KVL because we're solving for voltages, minus VL plus RO IO1, right? Because that's the current flowing through this RO resistor right here, plus RSIO is equals to 0. And then we can now plug in, so let's say this is our equation 3. So let's plug in equation 1 and equation 2 and see whether or not we can't get VO over IO. So we can solve for R out. So in order to do that, we consider then now minus VO plus RO. We know IO1 is this, so we can plug that in as IO minus GM VGS plus RSIO, which is equals to 0. We know that VGS, let me use red so it stands out. VGS is equals to negative RSIO. So let's go ahead and plug that in as well. So minus VO plus RO. Let's distribute this RO as well. So RO IO minus RO GM minus RSIO. I hope this makes sense. Plus RSIO is equals to 0. Minus and a minus gives us a positive, so that's a plus. So next, we can consider then that VO is equals to IO. So we're going to move this VO to the right-hand side, and then we're going to pull out IO, and we're left with RO plus RO GM RS plus RS. So then now R out, which we said was equals to VO over IO, is equals to RO plus RO GM RS plus RS. And this is essentially equals to 1 plus GM RO. So I'm going to pull out the RO from this terms. Sorry, I'm going to pull out the RS from these terms. So I'm left with RS times 1 plus GMRO, and then I'm left with a plus RO. So this is my output resistance of this circuit here. So I hope this makes sense. And you can consider that it's in parallel with RD, if you consider RD. So this is in parallel with RD. Now, lastly, let's figure out the AV gain of the circuit. I'm going to do it to the right here so that we can kind of see the circuit configuration. I'm going to go ahead and erase some of these loops because I want to show you in real time what it looks like. And I'm going to use black so it stands out. So consider AV is equals to VO over VN. Again, we consider that IO is equals to negative VO over RD. And the reason why this is negative is because you can consider that the current is flowing here into the negative terminal. So we can consider 0, and this is a VO. So 0 minus VO over RD is equals to IO. So that's why this is negative. The next thing we need to consider is VI is VN. Again, imagine we do a KVL here. And again, this for the AV gain, V out, VN is no longer equals to 0. So we can consider, we can consider the loop here, and that's equal to VN, right, plus VN plus VGS. This should be minus VN plus VGS plus RS IO, again, is equals to 0. If we solve for VGS, so if we solve for VGS, we would get that this is equals to VN minus RSIO. And since we want that our AV to be in terms of VN and VO, we want to get rid of this IO here. So we're going to go ahead and plug this into here. And we're going to say that VGS is equals to VN minus RS times negative VO over RD. Again, this is a negative and a negative, so it's a plus plus. And let's consider this our second equation. This was actually our first equation up here. Now the last KVL we need to consider is the KVL again along this path. So we consider that minus VO plus RO IO1 plus RS IO is equals to 0. And we can consider that this IO1, right, because there's IO1 here, from here is equals to IO minus GM VGS. So we could just go ahead and plug this in again here. And we consider this to be minus VO plus RO times IO minus GM VGS plus RSIO is equals to 0. Again, this is going to be minus VO plus ROIO minus ROGM VGS plus RSIO is equals to 0. So let's go ahead and plug some things in here for IO and for VGS. We know IO is equals to negative VO over RD. So we're going to go ahead and plug that in here. And we know VGS is equals to this equation here. So we're going to go ahead and plug that in here for VGS. We're also going to plug in IO in here as well. So this gives us, let me use blue, minus VO plus RO minus VO over RD minus RO GM. I'm gonna go ahead and plug all that entire equation. This is VN plus RS over RD VO plus RS minus VO over RD is equals to 0. And then now we get minus VO minus RO over RD VO minus RO GM VN minus RO GM RS over RD times VO minus RS over RD times VO is equals to 0. Now we can go ahead and move everything with a VO to the right hand side. So this term, this term, this term, and this term all go to the right hand side. And we're left with VO 1 plus RO over RD plus RO GM RS over RD plus RS over RD, and this is equals to VN minus RO GM, and this is this term right here. It stays negative. And so we have our answer, right? So this is going to be AV is equals to VO over VN, right? And in order to get this, this is the numerator, right? So we're dividing this over. So this is VN, and we're dividing this over here. So this is the numerator minus RO GM over, I made a mistake here. Oh, no, I didn't. So minus RO GM over 1 plus RO over RD plus RO GM RS over RD plus RS over RD. And what we're going to do here is we're going to multiply this right hand side by RD over RD. So then AV is equals to VO over VN, which is equals to minus ROGM. 1 times RD is RD plus RO plus ROGM RS plus RS. And this is your final gain. But when you're doing small signal analysis, it's good to do this once and understand how to get this. But then when you're trying to estimate more complex circuits, we consider a lot of simplifications. For example, a simplification what we consider is when RO is much greater than GM RO RS, and this is much greater than RD, and this is also much greater than RS. And I made a mistake here. This should be an RD here. So basically, when RO is the most dominant term in the denominator, we get that AV is equals to negative. Imagine if RO is infinity over GM RD over, again, imagine this RO is infinity. Infinity plus all these other numbers is just infinity. We can basically cancel out these two, and we're left with minus GM RD. So the AV gain of this circuit right here is equals to minus GMRD when you simplify it. So I hope this makes sense. The next video I'm going to be doing is the BJT equivalent. So it's going to be the NPN common emitter BJT with emitter degeneration. So make sure to look out for that. Also, if you have any questions, please leave them down in the comment section below, and I'll make sure to respond to them. Again, please like, share, and subscribe to my channel. Thank you.